This is our first example video for topic 2, and it's a projectile motion question, which might be a little bit more challenging than some of the ones we've done to date. I guess we'll find out. So my diagram, I'm actually not going to draw a picture of an archer with a bow and an arrow. I'm going to draw more of a graph. So we've got the x direction and the y direction. We've got the fact that the archer fires the arrow at an initial velocity of 56.7 meters per second at 23 degrees. I've drawn that a bit more to look like 45 degrees, but in fact this is 23 degrees. So that's the arrow, and it's 56.7 meters per second. That's the initial velocity. Now we know that the arrow is going to do a parabolic path and come down over here somewhere. So we want to know the maximum height reached. Let's call that y max rather than h. So the maximum height that it's going to reach. And we want to know how long it takes from start to finish until it gets to the end. So the first thing we want to do is divide. Remember that the whole key to projectile motion is dividing out the horizontal and vertical components. So we want to find, this is u overall, the initial velocity, but we want to find u in the x direction, the horizontal component, which is just going to be u cos theta. Because if you think about it, there's our angle. If we make it into a right angled triangle, then cos is the adjacent side, so this is ux. Cos is adjacent over hypotenuse, and then we rearrange cos theta to get that expression for ux, and uy is going to be that, which is the same height as that. So this is uy here, and that's the opposite angle to the hypotenuse, which is sine. So let's just do those in parallel. So uy equals u sine theta. Sorry, the app is trying to help me a little bit. Equals 56.7 cos 23 equals 52.2 meters per second. And in this case, 56.7 sine 23. I do apologize for the messiness. It's an artifact of the technology that I'm using, which is 22.2 meters per second. Does that make sense? It kind of does. The angle is 23 degrees. It's lower than I've drawn it there. So most of the velocity is in the horizontal and less of it's in the vertical because the angle is quite low. I hope that's relatively clear. Now we know also that for projectile motion, ux will stay constant. So Vx will be equal to Ux. It will just continue at the same speed in that horizontal direction because we ignore air resistance. A Uy will change, and in fact it will start at 22.2 at the start, and at the top, at Y max, it will be equal to 0 meters per second because you had an upward velocity and then you start having a downward velocity. So at that point, there's an instantaneous moment when the velocity is 0. Now, incidentally, I have started off considering upward to be positive. You'll see uy there is positive 22.2. So we've kind of implicitly defined upward as positive and downward as negative without actually saying that we did. To find the time, the trick with this is to divide the travel, the flight, into two pieces, because it goes up and then it goes down. It's under constant acceleration, so it ends up that the two halves are the same length. So as long as we remember what we're doing, if we divide it in half, now at that maximum time, at that maximum height, Vy, the vertical velocity, is going to be 0. Now, so what we're actually doing is we were asked, find the flight time and the maximum height. So we're doing the flight time, trying to find out how long it will fly. So if we take Vy just in the y direction equals Uy plus AT. Now the acceleration is going to be the acceleration due to gravity, but we've defined upward as positive, so that's going to be negative. We can rearrange that and turn it around, so just doing the algebra, t equals Vy minus Uy over A. Now Vy we said was going to be 0. The vertical velocity at the top of its flight is 0. The vertical velocity at the start is 22.2. 22.2 meters per second. The acceleration, remember, is going to be negative 9.8 because it's in the direction opposite to the direction that we've chosen as positive. And so that's going to be minus 22.2 over minus 9.8, 2.27 seconds. So that's the flight time for half of the flight. So we have to double that to get the overall time. So T total is, what's twice that? 4.54 seconds. That's the overall flight time from when it launches to when it hits the ground at the end. To find the height reached, the maximum height, we can use another of our equations. We know the initial velocity in the vertical direction. We know the acceleration in the vertical direction. So what we want is, what did I say? Y max. But Y max is just going to be equal to a distance, so it'll be an S, and we don't know what it is. We're using distance in our normal equations of motion. What have we got? We've got that Uy equals 22.2 meters per second. We've got that A equals minus 9.8 meters per second squared, and we've got that T to the top, not all the way, is 2.27 seconds. So that looks a bit to me like an S equals UT plus a half AT squared problem, right? We've got UA, T, and S. So I'm going to do the same thing here. Y max, which is what we're actually trying to find, equals S equals UT plus a half AT squared. Now remember that the U we're interested in is Uy, that vertical direction. So equals 22.2 times 2.7 plus a half times minus 9.8 times that should be 2.27 there, 2.27 squared. And overall, that means that Y max, the maximum height reached, equals 25.14 meters. So the arrow flies for a total time of just over 4.5 seconds, and at its maximum point, which is half of its journey, it's at a height of 25 meters.